Christmas is coming. December started. Darkness is over us. And your escape from introductory statistics is just around the corner. The plan of this lecture is, as I have announced, I'm going to summarize everything to you, basically within the first 45 minutes, and maybe a bit of the second part, depending on how it goes. Then I'm going to spend just very few minutes on the evaluation. I think I should. And some perspectives, and then some exam talk. I guess that's probably where we are in our minds a little bit now, heading towards the exam. Let me start. I prepared this summary presentation for you. 27 slides, including all the heading slides. I'm going to put it into 3 parts that goes with the topics, actually. I'm going to make distinction there, and I'm going to make a distinction here. So these are the 12 lectures, the 12 days, and the titles of those days. The first 3 days of the course, we did the basic sort of data and probability. Then we spent 4 days in the course doing 1 and 2 sample statistics. If I'm going to say it with a few words, 1 and 2 sample statistics, means and variances, with and without normal distribution, right? We turned to this simulation, and we had some idea that this simulation idea, actually, is a very broad one that could take us much further. And then the rest of the course, the last 5 days of the course, we took what we learned. We used the 4 middle days talking about 1 and 2 sample situations, the most simple ones that we can meet out there. We used that to teach you the ideas of statistics, right? Confidence intervals, hypothesis testing, and sometimes the planning idea. How do we get large enough experiments to meet the goals that we'd like to meet? But we do that in the simplest of all contexts, 1 sample and 2 sample data, right? Then 8 to 12, the chapters 5, 6, 7, and 8. We start to extend the different situations and complexity levels of where we can do the statistics, right? Not only 1 and 2 samples, but more samples and regression and two-way data and count frequency data. All new situations that real life work as an engineer you will need to know about these situations and be able to deal with them, right? So, here it comes. We started out where we started in 2nd grade of elementary school. If you get some data in an Excel sheet or you tap them in yourself, we shouldn't stop, even though we become advanced engineers, we shouldn't stop every now and then looking at the data as they are. It's a good start, right? We shouldn't forget that. Way too often people look at the advanced methods and forget to look at the raw data and have a feeling of what's going on. So, that's what we started out with in chapter 1. We should still do means and standard deviations, box plots, medians, upper, lower quartiles. These are all the things that you're expected to know about and know how to find, right? Remember the link between the quartiles and the box plots, right? You should know about the box plot. Here's just sort of a hand version of it. You should know about this Q1, the median, and Q3 thing, and what the definitions and what they mean, right? Actually, one thing that I could have added also was that we also learned that we could already back then, that we could quantify the relation between 2 variables by a correlation coefficient. I told you that already before we even discussed all the regression thing that came later. Just as an explorative measure, descriptive measure, we could compute the correlation coefficient, and we call it R. So that is still important in this course, in the rest of your engineering life, right? We should still look at the raw data. That's the starting point of statistics. That's the data. Whether it's big data, that's the buzzword today, or it's small and precious data, as I then usually say. Because even though this world is very much big data, it's also still small and precious data. I assure you, Novo Nordisk produces a lot of small and expensive precious data that they'd like to have analyzed in the optimal way to gain all the information, all of those expensive investments in creating such data information about the product development they do. Statistics is about more intelligent look at the data than just look. We still look at them, but we should be more intelligent. That's the whole purpose of this course, to make us be intelligent about the way we learn from data, right? And I've tried to convince you, and I'm sure you are being sick and tired of me trying to tell you about, probably because now you know, and maybe you knew before you came, that learning from data is basically a condition of all of our lives. Privately and very much so professionally as an engineer that you will. And it really doesn't matter what kind of engineer you're going to be. You're going to live with the fact that you and your colleagues in your company or your institution are going to live in a world of trying to learn from data. It's going to be part of your life. We cannot change it. We could move outside, dig a hole in the earth and live there if we want to change, but otherwise not. Probability is the way to be intelligent about looking at data. That's why we need to learn just a little bit about probability in this course. You can learn much more about probability, and that's good for many reasons, but we have tried to do it at a minimum in this course to make us able to do the statistics that we'd like to do within an introductory stats class, right? You should know that. I know it's not popular to tell you all the things you don't know, but I think it's very important for your work as an engineer that you know what you know and you know what you don't know, right? So that's also important to know the limitations of what you know. What did we learn? Discrete distributions. Definition of a stochastic variable. We use the capital X. We distinguish the stochastic variables, the random variables, from the observed ones. We talk about random systems, randomness. For instance, in this discrete world, the binomial distribution that we've probably all met before we came to this course. If we meet something random in our lives, in our professional lives, we need to try to be in control of this randomness. Well, it's an inherent thing about randomness that if you cannot control the randomness part of it, because then it would not be random, right? But the only way you can be in control of a random situation is to know what are the probabilities of various potential events that could happen, right? So your way to be in control of randomness is to know the probabilities. So knowing probabilities is what makes you intelligent, right? Knowing what could happen under certain conditions and assumptions. That's why the mathematical theory provided us with a tool to know probabilities. They call such a collection of probability is called the density function, right? It's the collection in the discrete world of all the probabilities which are there. So in a situation, if I know all the probabilities, I'm fine. Now there is another way to know all the probabilities. We could also express all the probabilities in this a slightly more indirect way by talking about not the specific probabilities, but talking about the left-hand side probabilities, if you want. That's another collection of probabilities which don't give them directly, but give them indirectly. So if I know the density function, I could extract the distribution function, and if I knew the distribution function, I could find the density function, right? They are sort of alternative characterizations of the set of probabilities in a random setting. Knowing that, We could also talk about means and variances, about, in general, random systems. That is good to know that we can also mathematically define what we mean by a mean and a variance. I mean, if we have some data in an Excel sheet, that's what we learned the day one, then I can compute the average and the sample variance by just plugging this into the simple formulas. But there are also concepts in general modeling of random systems that can tell us what do we expect on average from a random system and how much could a random system vary from time to time, right? We have those concepts in place. We have defined them. It's kind of taking the average over all the possible outcomes, weighing with the probabilities. I'm not going to show you all the formulas now within those 40 minutes. And we could also weigh together all the squared deviations by the probabilities, and then we get the variance. Here's the thing, the variance in itself actually is an expectation. That's a concept one has to maybe get used to. The variance is the expected squared deviation. So it's also an expected value, but it's an expected value of something else. Not of the original x, but of the squared deviances, of squared differences to the mean. In the discrete world, means and variances are sums, right? Where we have all the probabilities entering the sums as weights. We saw some specific ones. I already mentioned the binomial. There is the hypergeometric and there's the Poisson. 3 specific named probability distributions for us to work with in different contexts. Most of the course, we actually talked about quantitative, most often continuous type phenomenon, right? If we measure concentration of something, it's really a continuous phenomenon that could have all sorts of values between 0 and a high number. We don't know the limit typically. So we need to be able to deal with probabilities. That are continuous, like this. Such that the density function is now continuous. This is where we have the distinction between the continuous and the discrete world, right? Because in the continuous world, the probability of individual points is 0. There is no area under one point on such a curve like this. So the only way, in a way, the definition of the distribution function by probabilities looks exactly the same and is the same. There's no difference. If we call that capital F, the density function, in fact, this is not good, is the derivative of the distribution function. Gandalf, should we consider going to the VGA instead? I have another cable. Is it falling out in your place also, or just on the screen? Yeah, it's not. I'll just try the other cable. Which one was which now? Try this one. Let's see. Try to make the best of it. The only way we can combine probabilities with the density function is by means of areas under the curve, right? So the density function in the continuous world describes, that was my fault, describes probabilities by looking at areas under the curve. We still have mean and variance definitions now defined by integrals instead of sums. And we can also talk about, those rules, they were actually given to us. They worked both for continuous and discrete distributions. For instance, one of the rules was something like this. I'd like to emphasize that. The variance of a linear combination of k of those was the sum of those ones times the variance of the individual ones, right? Important rule. Very, very, very important rule. This is the rule that gives us the tools for doing statistics in a way, that if we use that on an average, where all the a's are 1 over n, it turns out that the variance of an average becomes the original variance divided by n. This is what makes precision in statistics going to 0. This is why it can be worth the investment in a company to put more money in having a higher n, because the precision increases, the variance decreases with n, right? That comes from this variance rule. Very important in a way. But we see it in many versions later on, so in a way maybe we don't have to worry about the original rule, because it goes into all the formula of confidence intervals and all. You see later that the n makes confidence intervals become small, and that's good, but it can be expensive. Specific distributions very much show the normal. The normal plays a central role for many reasons, but there are other than normals. Original data distributions are often in real life not normal. They may be, many of them are, but not all of them. So we have to sometimes work with non-normal distributions. And there are situations that, for instance, the exponential distribution we saw nicely used for waiting times, for instance, or reliability observations, lifetime of either components or people if you're in the bio area. So that was the continuous distributions. This was the first part, Gandalf. So